One of the common problems that is seen in high-speed designs is the crosstalk. Crosstalk occurs due to the unintentional coupling of energy from one signal to the another. Like, let us assume there is a driver and there is a receiver and there is a trace that is routed between them. And let us assume there is one more driver and there is a receiver to which the signal is routed. So this is a trace 1 and this is the trace 2, and if there is energy that is being coupled from one signal to the another, then such a scenario is called crosstalk. So why does crosstalk happen? So before going into it, we need to know two terminologies while when the crosstalk happens. One is called a victim. This is a very important terminology. And the second one is called aggressor. Okay, what is victim? What is aggressor? In these two signals, okay, there is a guy whose energy gets coupled onto the other's trace, right? So the trace whose energy gets coupled to another trace is called the aggressor, which causes the crosstalk, and the second trace is called a victim because this is a victim of the crosstalk. Now, this crosstalk between the two traces happens due to two scenarios. One is mutual capacitance, okay, mutual capacitance, okay, and the second one is mutual inductance, okay, inductance. Okay, so one is mutual capacitance and second one is mutual inductance. So mutual capacitance is something that happens between the traces, and mutual inductance is also something which happens between the traces. So what is actually mutual inductance and mutual capacitance? Let us have a look. We know a capacitor is nothing but two plates, two electrically conducting plates separated by a dielectric. Okay. Now, when there is a some variation of energy here, it passes to the other plate as well, right? Now, this particular scenario, if you see here, there is one trace and there is another trace. In between, there is a void which we can consider as a dielectric between these two traces, and this actually, if we see, is forming a capacitive kind of effect, right? Now there is some energy on this trace, there is some energy on this trace, but definitely there is some electrical voltage difference between these two, right? So because of these, there is electric field that is developed which couples onto this, similar to what happens in the capacitor. Okay, now this coupling causes this signal to vary unintentionally. So that scenario which we see here is called a mutual capacitance. So mutual capacitance basically happens due to the electric field coupling that happens between the traces on a PCB. Now, what is mutual inductance? So, these two traces basically, let us assume, are traveling together over a particular distance. Now, this particular signal will have magnetic field around this particular trace, right? As the signal is moving, as the other signal, the victim is moving along this aggressor over a particular length, this magnetic field couples onto this victim from the basically the aggressor to the victim, which causes again variation here. So as we know, basically, if there is some particular variation in one trace, the magnetic field around it causes current in the other trace as well. A simple law called Faraday's law, which we studied, right? So that is one of the reason for mutual inductance happening. So these two are the scenarios which causes the crosstalk to happen in PCBs. Now, what we need to do to avoid this crosstalk? So, to avoid crosstalk, one important point is increase the distance as much as possible. To reduce the capacitance, what we do basically we increase the distance between the electrical plates of a capacitor. Right? Similarly, in PCB, increase the distance between the traces as much as possible. Now, one of the biggest challenge that we face in PCB designs, especially in the high density boards, we cannot increase as per our convenience, right? The board has a high dense components around, and we have to live with some of the coupling. So, in these scenarios, ensure that there is proper ground plane around this very closer than the distance, such that the energy couples more onto the ground than to the signal. This is one implementation that can be done, and this is one of the hardest. One of the generic way of doing it. One of the hardest way of doing it is in between two traces. Try to stitch some ground wires to the ground plane, switch some wires to the ground plane such that there isn't any coupling that is happening. So this cage that we form here, these wires that we add here can be done only in boards where you have that much space, which is not the case in high density boards that we are talking, right? So this is a non-practical thing which can be done. But if there are traces which are isolated away from other things and there is enough space, we can do this as well. And we can also increase the space between. So two different things which can be done, right? In the olden days, now we have strip line, micro strip line routing. In the olden days, people used to route the traces perpendicular to each other in different layers, such that there is no coupling between them. So that is one technique which was followed. So nowadays, there isn't any orthogonal routing that is done in different layers. So this is again a hard technique which was followed in olden days, which is not followed now. And another important thing is ensure that in case if you cannot avoid, you cannot have this scenario, you cannot have this scenario, you cannot have this scenario. One other option is to avoid having two traces run parallelly for a longer distance. This ensures that there is minimal coupling. Like if there is one line, take another line and move it away from the trace, and again you can move it nearer again. So this is one technique which PCB layout engineers do follow in their layouts to ensure that the signals are not routed parallelly a longer distance. So that is one scenario, right? So these are the different things in crosstalk. We will talk about crosstalk, near and crosstalk, far and crosstalk. There are other things in the next videos. Thank you.